Ladies and gentlemen, last week we began studying the physics of motion, which is called kinematics. But many of you probably noticed that we were only studying motion in one dimension, okay? And many of you maybe had the question like, well, what about things that move in 2 dimensions or 3 dimensions, which is almost everything. Very rarely does something ever move only in 1 dimension, and that is true, okay? But the reason why we didn't study that last week is because we need a whole other kind of mathematics called vector mathematics to be able to talk about how motion breaks down in more than 1 dimension, okay? So I'm going to name it and I'm going to say it. This lecture, unfortunately, we're stepping away from physics for a second and stepping into math, specifically the mathematics of vectors, okay? And I know this wasn't a math course and I know you didn't sign up for it, but unfortunately, it's necessary, okay? So I'm going to start by saying that I will do my best to make this as clear as I possibly can, okay? And to make it as entertaining as I possibly can, okay? So here it goes, the mathematics of vectors, okay? All right, so if you guys could click ahead to the quote of the week. It says, in the end, these things matter most. How well did you love? How fully did you live? And how deeply did you let go? And this was said by one of my favorite meditation teachers, this guy named Jack Kornfield. And I don't think this one needs a heck of a lot of explanation. I think it's something that we all intuitively kind of know and understand, and just sometimes need to be reminded of, okay? So that's what I'm doing. All right, if you guys could click to the next slide, we're going to start talking about the 2 different kinds of quantities that we measure in physics, okay? One of those quantities is scalars, and one of those quantities are vectors. Some of you might have an intuitive understanding of these already, but if not, I want to totally be clear. Okay, the first set, if you guys could click one slide ahead, is scalars. Okay, and scalars are numbers that just require a magnitude. In other words, you only need to say how big they are in order to define them. A great example is time. Okay, like this video will probably be somewhere between 5 and 10 minutes long, right? But I wouldn't say, oh man, this video is 5 minutes north. Wouldn't make any sense, right? You wouldn't even think to associate a direction with it. That is a scalar, okay? And I have 6 pictures on here that show 6 prominent scalars that we study in physics, okay? The very first one, you see this like little weird psychedelic clock thingy. That is obviously time. Time is a scalar. You don't need a direction to define time, right? Next to that is speed. There's a little speedometer there, right? Speed is always just an absolute value. You do not need to know the direction to know speed. It's simply what is the rate at which you're covering ground or changing position, okay? Next to that is a looks like a little blood pressure situation. Pressure is another scalar quality. And then we go down to the bottom left-hand corner, and we have distance, right? The distance between those 2 cities. And distance is also a scalar quantity, okay? Which is different than displacement, which we'll talk about in a second. That is a vector. Next up, we have these 2 forms of renewable energy, wind and solar. Energy is also a scalar quantity. You would never say, oh man, like I just had a burger that had, 300 calories west, right? It wouldn't make any sense. And then next to that, you have a thermometer. Temperature is also a scalar. You wouldn't say, oh man, it's really hot today. It is 95 degrees to the right? So scalars, simply because it wouldn't even make sense to associate a direction with them, okay? All right, so if you advance one slide to vectors, this is different than vectors, which are qualities that you absolutely need a direction in order to fully define that quantity in order to make it make sense, okay? So top left-hand corner is an airplane. That's velocity, right? Obviously, you absolutely need to know the direction for velocity in order to fully understand what's going on. So for example, I start here in San Diego, right? If I'm in a plane and I don't clarify my direction, I just say, go 32 meters per second or whatever, then I don't know where I end up. Not having direction associated with a velocity is the difference between winding up in, Moscow or, Portugal, right? Very, very different outcomes based on not having a clarified direction, okay? Next up there's 2 people pushing a ball. That's forces. Obviously, forces need a direction if you want to know what the outcome of what's going to happen, right? So it only makes sense if you say you apply like a 10 Newton force up, right? Because then you know the object's actually going to be accelerating upwards, right? If I apply a 5 Newton force to the left, it goes to the left. If I apply a 5 Newton force to the right, it goes to the right, right? Makes a big difference, okay? If I apply a 5 Newton force up, you get the idea. Okay, next up is the little foot on the accelerator. That is obviously acceleration. Guys, you need to know which direction you're accelerating in to know which direction you're actually changing your velocity. Very, very important to know your acceleration. Acceleration of forces are usually related, right? They're in the same direction. An applied force will cause an object to accelerate in the direction of that force. So those guys are linked. And then lastly, that screwdriver or that wrench turning is torque, which is also a vector, which we'll talk more about later on. Okay. So that is the difference between scalars and vectors. And I have one slide, the next slide, which talks about displacement, which is the simplest vector. I want to start there. As I said before, displacement is simply the difference between your starting point and your ending point. Okay. But there's a very specific direction that vector will go, right? If I, for example, start here and end here, then I have a vector pointing from here to here, right? Whereas if I start here and end over here, I have a vector that points from here to here, right? So when you're talking about displacement, direction is absolutely important. All right. Now, vectors have, as I said, a whole mathematics that's associated with them, okay? And they also have kind of a notation, a nomenclature, so that you know how to express vectors, so that it's easy to add them, multiply them, subtract them, etc. Okay? So in the next video, we'll begin talking about vector notation and how to begin simple operations with vectors. I'll see you there.